So tropical geometry is algebraic geometry over the tropical semiring. It's the reals, union, infinity, and we have addition, legion. So the tropical sum A plus B is the minimum of A and B. Last time I talked, I used maximum. You can use whatever you want. Today we're going to use minimum. And then the tropical product A times B is A plus B. Note that the additive identity is infinity and the multiplicative identity is 0. Then we have tropical polynomials.
Today minimum is conformable because we're going to deal with the series.
Yeah, we're going to talk about valuations, so minimum makes more sense today, which I think also makes more sense with
But I think because we are going to deal with the series.
I think so. It just made more sense with minimum today. So tropical polynomials is finite sum of tropical monomials. And these correspond to piecewise linear functions. So, for example, we can look at x squared plus 1 times x plus 5. And so this is equal to the minimum of 2x, because x squared is x times x, x plus x is 2x, x plus 1 and 5, which, if you graph this, it's going to look like 2x, x plus 1, and 5. Not super to scale. You would take the minimum of all these lines, and this is why these tropical polynomials correspond to piecewise linear functions, because we're taking the piecewise of these lines. These points where two lines meet are called the roots of the tropical monomial, or polynomial. Those 2 points. Okay, another example that we can look at is 0 plus x plus y. This is the minimum of 0, x, and y. We can't graph this the same way. We're going to look at what we call the tropical plane curve. Which we denote via P, and that's defined as xy in R2, such that the minimum is attained at least twice. And we saw in my last talk that this plane curve for our tropical line looks like that. also going to remind you about Newton polygons and Newton subdivisions. Our Newton polygon comes from our integer lattice. So for this example, the Newton polygon has vertices at 0, x, and y. We take the convex hull of those, and we get this Newton polygon. And then from there, our tropical curve is dual to our Newton polygon. So we get this, which would be our curve if we were using maximum. Since we're using minimum, we have to flip it by letting x be negative x, y be negative y. And so we get the same tropical line that we got over there. You can extend this to Newton subdivisions, which I talked about last time I talked about it. We're not going to talk about that today. But we need to talk about primitive vectors and weights. And so the weights for our different edges is the lattice length. Of the Newton polygon or Newton subdivision. So in this case, the length for all these sides is 1. So all of these edges would have weight 1. The primitive vectors are vectors perpendicular to the Newton polygon outward, and the primitive vectors have to have GCD of the coordinates equal to 1. And we're going to take a step back from that for a little bit and look at field of Puiseux series. So this field helps us connect regular algebraic geometry with tropical geometry, and we denote this field like this, and it consists of formal expressions of the form T, which is equal to C1 T to the A1 plus C2 T to the A2, and so on, where we need our CI's to be in C star, and our AI's are rational, and we need AI to less than AI plus 1. So our powers are increasing. And then we need a set of all exponents to have a common denominator. Yes?
Do we require our exponents to be positive?
No.
Okay.
We're going to do some examples.
It's a field, so also there will be
Examples. We could have things that look like C of t is 1 over t plus t. We could have C of t where we have t to the 1/3, plus t to the 1/2. You could have sum from I equals 0 to infinity of t to the I. Some non-examples, things not in this field, would be something like t to the square root of 2. So you don't, because that's not a rational exponent. Question?
Yeah, so it looks to me like the way this is written, you could have an infinite number of positive exponents, but you're limited to having a finite number of negative exponents.
You can have infinite negative exponents too.
How do you do that with that indexing?
Like t to the negative 1 over I, that's how it goes from.
But like you're saying that they're in increasing order.
So t to the negative
Yeah.
1, negative 1/2, negative 1/3, negative 1/4.
Oh, I
Just
see.
have a common denominator. With the common denominator,
Like the Laurent
you could only
series,
have
but we
finite
have
number.
rational exponents.
What do you mean by having common denominator for 1/3 and 1?
You could write these as 1/2/6 plus 1/3/6.
1/2/6?
You could write this with a common denominator.
So I think Rick was saying that the last bullet point rules out infinitely many negative, or the last two together rules out infinitely many negative exponents.
It's probably true, you can only have finitely many exponents below any certain number.
Right.
Pick a number, only have finitely many below that, because there's only finitely, once you have to start somewhere, and then there's only
Yeah.
finitely many things with whatever common denominator is available is only finitely many in that interval.
So one more non-example would be sum from I equals 1 to infinity of t to the 1/I. Because that covers going to be increasing. Okay, any more questions on this field?
Okay. Maybe I'm just not understanding. What do you mean by having a common denominator?
They don't have to be written with a common denominator, but you have to be able to find one. You have to be able to write them with one. So,
So I know a common denominator for 1/3 and then 1/2 is 6.
yes,
But what do you mean by have a common denominator?
you have to be able to find one.
What wouldn't have a common denominator?
Something like
With this last example.
the last
last
one.
example.
Oh, yes, the non-example, okay.
It's like a bound on the
Yeah,
denominator.
it's like a bound.
The precise definition should be that there should be an integer, the denominator, such that that integer d times ai is an integer for all. That should be the precise definition.
Does that help, Jay?
So it's like LCM is finite, something like that? Or, I don't know. Maybe without.
Maybe, yeah. Maybe we need to do some more.
You have to have a finite number of denominators to have a common denominator.
Mhm. Yeah. So now I'm going to talk about valuations.
Is this a condition of common denominator, is this necessary in order to multiply such numbers?
I'm not sure.
In order to get sort of a finite number of contributions to any one exponent, is that the purpose of this?
Probably, because if you took that non-example and multiplied it by that last example, then I think you'd be getting not a well-defined.
You'd have an infinite number of contributions to the constant.
T to the 1, for instance. Yeah.
Okay.
Okay, evaluation on a field K valuation val from k to the reals union infinity such that the valuation of x equals infinity if and only if x is equal to 0. The valuation of x times y is equal to the valuation of x plus the valuation of y, and the valuation of x plus y is greater than or equal to the minimum of the valuation of x and the valuation of y, with equality if the valuation of x is not equal to the valuation of y. So some examples of valuations are the trivial valuation, which is the valuation of a equals 0 if a is not equal to 0. P-adic valuation, which for this valuation we want our field Q, and then the valuation, p-adic valuation of something of the form p to the n times a over b, where p does not divide a and p does not divide b is equal to n. So the power, highest power of your prime, you can write your number of this form as. So for example, the p-adic valuation of 6, you can write 6 as 2 times 3, so the p-adic valuation is 1. The p-adic valuation of 5/12 is -2, and the 3-adic valuation, do this with any prime, of 9 is 2. One more example of valuation is valuation from the field of Puiseux series to the reals union infinity. And that is defined by the valuation of 0 to infinity and valuation of C of t, where C1 t to the A1 plus so on is A1. So your valuation is your highest power. This is the valuation on the field of Puiseux series.
Lowest power, right?
Yes. Sorry. Okay, so the tropicalization of some f that is sum of ai x to the I in R, any field adjoining x, is trop over the valuations of our coefficients. And still doing our normal algebra. And so this is now in our tropical semiring matrix.
So K is or
Any
it
field.
doesn't have it's just a value at filled with the valuation.
And the same definition works if you also have like y to some power, and you're also doing y. And just add it. So, example, if our f is 2x squared plus 3x y plus 4 y squared plus 7x plus 9y plus 6. And we have our valuation is the 2-adic valuation. Then you figure out what our tropicalization of f is. We get 1 times x squared plus x times y plus 2y squared plus x plus y plus 1. I'm a little sloppy with my notation, but yes.
So the tropicalization is defined in terms of evaluation on the field K.
Mm-hmm.
Okay.
So K has to be a field with valuation. Now we can define, very similar to our tropical plane curve, the tropical hypersurface. Of our f, which is in some field going x1. This is trop the f some w in Rn such that the min in our trop f is attained at least twice.
So basically, V of trop F, which you write down, is it right?
V of trop of Vf.
So you write down trop of Vf, and then what you write down on the right hand side is trop of Vf. V of trop F. So trop F is a tropical polynomial, and then you write it from 0 to 7.
It's not the
Well,
zero.
not close to the zero.
It's not saying 0 7.
Yeah, it's not quite the same.
So you define V of a tropical polynomial, right? To be
Mhm.
this thing.
Is that a question, a comment?
That's kind of, like, so the right side of this is V of trop F, right?
So V of trop F is not exactly the same thing as trop of Vf.
Oh.
One is equal to the closure of the other.
Oh, okay.
But this is the tropical hypersurface definition. Okay. Example. F is kind of long, but it's cool, so bear with me. 8x cubed plus 2x squared y plus 2xy squared is 8y cubed plus 2x squared plus xy plus 2y squared plus 2x plus 2y plus 8. You can take the tropicalization of this. We're going to let valuation, p-adic valuation. Trop of f is 3x squared plus 1x squared y plus 1xy squared plus 3y squared plus 1x squared plus xy plus 1y squared plus 1x plus 1y plus 3. And the tropical hypersurface for this is going to look like so how you can think about this, and believe me that this makes sense, is this corresponds to our 3,
So what
our
you
1y, our 1x, our xy. So when 1y and 3 are equal, or when the min is attained by both of them, it would correspond to this part of the tropical curve, or the tropical hypersurface. And the fact that it has this loop tells us that this curve has genus 1. This hypersurface has genus 1.
Does that say anything about the surface defined by f?
I would guess that it would also have genus 1, but I don't know.
So a degree 3 curve in P2 is generally going to give you a genus 1.
Because it's an elliptic curve.
If you chose a different valuation, would that give you a different, can you say anything about how the hypersurfaces would change?
It probably will change because your coefficients are going to change, so your Newton subdivision is going to change. But I don't have an example off the top of my head.
I just maybe I forgot, but did you define tropical plane curve by also a minimum attained by at least twice? But what's different than what you wrote down on the right hand side?
We're starting with something that is not a tropical curve.
Okay.
Because before, when I defined it, f was a tropical curve, and now f is.
Okay. So this is a zero of trop of f?
Like the zero set?
Yeah, zero set
It's
of
like the
trop.
tropical equivalent of the zero set. So it's not quite a zero set because it's when the min is attained twice.
So before we also defined the tropical plane curve by minimum attained by at least twice. So this is also minimum attained by at least twice. So it's a zero set of a trop f. Is that correct? I'm sorry, I'm just confusing. So what's the
I don't think it's quite a zero set because it's not when the tropical functions equal to 0. But it's like the tropical equivalent of that in algebraic geometry.
I'll maybe ask him.
Okay. So, definition. So now we're going to focus on tropical curves whose new polygon is just a triangle, or some subdivision of a triangle. So a tropical plane curve that has degree d if it is dual to some subdivision of triangle with vertices at 0, 0, 0D, and D0. So example of this is if we go back to the tropical line, that was x plus y plus 0. That was dual to the Newton polygon with point vertices at 0, 0, 1, 0, 0, 1. So our tropical line has degree 1. We say that two tropical curves intersect transversely if they intersect in a finite number of points which are not vertices of either curve. So some non-examples, things that are not intersecting transversely, would be if you had a line looks like this, and then another line where their intersection is a whole line segment, because that's not a finite number of points. Another non-example would be we had this line and this line, because they're intersecting at a vertex. Well, an example of two lines intersecting transversely is like that. Okay, another definition. If we have two tropical plane curves which intersect transversely, at a point P, we're going to denote E1 as the edge of gamma 1 containing the point of intersection. We're going to let P1 be permanent vector in the direction of E1 And W1, the weight of E1. Similarly for E2, P2, and W2. We define multiplicity of intersection. These two curves at P to B mult P 1 by 2 to be the absolute value of the determinant of the x-coordinate of the weight 1 times P1 and the y-coordinate of that, and then the x-coordinate W2, P2, and the y-coordinate of that vector. We'll see an example in a second. Okay, so we have one line, and another line that are intersecting transversely. Then our primitive vector for the red one is going this direction, which is -1, 0. And we saw earlier that the weight of all the sides of the line are 1. So we know that the weight of that one is 1. This is P1. And then for the second one, go this way. So this primitive vector has direction 0, -1. Also has weight 1. So the multiplicity of intersection of this point is determinant of -1, 0, 0, -1, which is equal to 1. So these two lines are intersecting at a point P that has multiplicity 1. Okay, now theorem, which is Tropicalization theorem. Tells us that if we let gamma 1 be tropical curve of degree D1, and 2 be a curve of degree D2, assuming they intersect transversely. Then your intersection is equal to the sum along all the points of intersection. of the multiplicity of P at all those points, which is also equal to D1 times D2. And so if you go back to our line example, we saw that the degree of a line is 1. So degree of one line times the degree of another line is still equal to 1. So Bézout holds for 2 lines. We'll look at some other examples. If we want a quadric, we need it to be dual to some subdivision where the lattice lengths are 2. So if we take that subdivision, then we get a tropical quadric look like so if we take 2 quadrics, these are degree 2. Okay, there's one. There's another one. And we see that we have 4 points of intersection, which agrees with our degree of the one times the degree of the other. We can check that all of these have multiplicity 1, but we're just going to check that one of them. So let's pick this point. Then our permanent vector going this way is going to be -1, 0, and permanent vector going this way is going to be 0, -1. So we have the same, so I'm not going to write it out. But the multiplicity of all these points is 1. So then the sum is also going to equal 4. So we're good. But we can also have a quadric that has one of its edges having multiplicity 2. If we subdivide our new polygon differently, so we can have a quadric that has a shape like this, where this edge is going to be weight 2 because it's going through an edge of a Newton polygon that has lattice length 2. And if we take this curve and we intersect it with another red one, we have 2 points of intersection. But we have 2 degree 2 curves, so we need 4 points of intersection. We have the same primitive vectors, but now if we take the determinant of the one going down, so the 0, -1 has weight 2, so we would have 0, -2 to -1, 0. So this determinant, and so value determinant is going to equal 2 for both of these points. So we still have 4 points of intersection when counting with multiplicity. So Bézout's theorem holds. Those are all the examples I have. Any questions?
Quick question. So it seems like in that first example, it's super nice because you like subdivide your Newton polygon into a whole bunch of like triangles. Like it's like a triangulation. Is there anything to say about like, are the triangulized subdivisions correspond to like nice intersections? Nice meaning like the points of multiplicity 1?
I think they correspond to the most general, like, quadrics or scaled up. So they're not going to have any edges with way more than one.
Okay. Every subregion is triangle?
Yeah,
And the
every.
curve is smooth, I think. As far
Yes,
as I
that's true
remember.
too. That's true too.
Okay.
What does it mean for a tropical curve to be smooth?
If the subdivision is all triangles. That's all I know.
So equivalent, so we can
All
define.
all triangles of minimal area.
Yeah, all triangles vary 1/2. Sorry. I'll let you know when I figure it out. Any other questions?
So you said earlier that tropicalization v of f and v of the tropicalization of f differ by closure.
Yes.
Can we see like where the difference is? Do you have an example?
No, I don't even remember which one you need the closure of.
Okay.
But I can figure that out later.
Oh, why did we introduce Puiseux series?
Because it's one of the valuations that you see used a lot when you're switching over to
So you
tropicals. When
might
you're taking a
have-
tropicalization, I see they use Puiseux series a lot for that.
So you often take tropicalizations of polynomials whose coefficients are
Polynomials.
weird.
Yeah. But those are gross, so I didn't do it.
All right, let's thank Erin again.